Part of a series of videos I'm making to support a course that I'm teaching in introductory proof writing. And here we're going to start looking at proofs involving sets. Before we get started, I want to recall set builder notation, which is like a nice quick way to easily write a set down or what the elements of a set look like. So we have a set A, which is written in set builder notation like this. So we've got two curly braces. Then we've got a line down the middle. Sometimes that's a colon, and that represents the word such that. So over here on the left-hand side, you have the general shape of an element. Sometimes you really leave the general shape out, and you just put like kind of a symbol to represent the element, and the general shape is via context. And then over to the right here, you need to have the rules that the element must satisfy in order to be in the set. Now we could write that via the notion of a mathematical statement like this. So here we've got A is equal to X in S. So S would be some larger set that represents the general shape of the element. Or sometimes you just write X here if it's kind of understood what universe you're working in. Such that P of X. And this P of X is some mathematical statement depending on X. So in a previous video, we looked at the definition and a bunch of examples of mathematical statements. So I'll let you guys check that out if you want to. So we're going to look at three things in this video: how to show something as an element of a set, how to show that one subset or one set is a subset of the other, and how to show that two sets are equal. So to start off, I want to give you guys an outline for a proof that some element is inside of a set. And so how do we show that A is an element of capital A, where capital A is defined like this? So its general shape is that it's in some larger set S, and then it satisfies this mathematical condition P of X. So generally, you've got this first really easy step, which is checking that A is in S. In other words, it has the right general shape. And then next, you want to argue that the mathematical statement P of A is true. And then as long as you have those two things, then you've shown that A is in this set capital A. So it has the right general shape and it satisfies the correct rules. Okay, so let's look at a couple of quick examples. So for the first one, we're going to show that 3 is in the set of real numbers that are between -2 and 5, including -2, but not including 5. So notice we could like write this in interval notation as bracket -2 and then 5 parentheses like that. So this is super clear, and you wouldn't really need to write a proof down for this, but just for the sake of the video, let's see everything that you would need to do. So first, you would check and notice that 3 is a real number, and that 3 is bigger than or equal to 2 and less than 5. So in other words, it has the right general shape and it satisfies the right specific rules. Okay, let's look at one that's a little bit more interesting, although still pretty clear. And that is 24 is an element of the subset of natural numbers such that 3 divides in and 4 divides in. So the general shape is natural numbers, and then the two rules that must be satisfied are that they are divisible by 3 and divisible by 4. Okay, so let's check that. So maybe we would first notice very clearly that 24 is a natural number and that 24 equals 3 times 8, which also equals 4 times 6. So the fact that it equals 3 times 8, that means it's divisible by 3. The fact that it equals 4 times 6, that means it's divisible by 4. And in my mind, that's really enough to show that 24 is an element from this set. It's got the right general shape and it's got the right, specific rule being followed. Okay, so next we've got this set containing 97 and 394 is an element of the subset of elements from the power set of the natural numbers that contain 2 elements. So let's recall that the power set of natural numbers is the set of all subsets of the natural numbers. So what we're looking at here is the set of all 2 element subsets of the rational numbers. So what we're looking at here is the set of all two element subsets of the natural numbers. So very, very clearly, 97, 394, the set containing those two elements is an element from this set. It is a subset of natural numbers and it has two elements. But notice, something like this, the number pi, is most definitely not an element of this. It's not the right shape at all. So that's a real number. That's not a subset of natural numbers. Furthermore, something like the singleton 1 is also not a subset of this. It's got the wrong number of elements. Okay, so let's maybe get rid of this and then we'll look at showing one set as a subset of another. So now we're ready to move on to showing that one set is a subset of another. So let's recall the definition for that. So we say A is a subset of B and we write it like that. If for all A in A, we have A is in B. So that's the definition of being a subset. So let's see how you would prove that. So let's say we've got this proposition, which is A is a subset of B. Now, before I give an outline for a proof, which is really a generic outline, I want to point out that this is really a conditional statement. And the conditional statement is that if A is in A, then A is in B. So that's like a P implies Q kind of situation, where P is the statement A is in A, and Q is the statement A is in B. So we already looked at proofs of conditional statements using lots of different techniques: direct proof, contrapositive, contradiction. So in fact, you can just treat this as a proof of a conditional statement and use any of those methods that you want. Although most of the time, a direct proof method will work the best. And since that's the case, that's the outline that we have here. So you want to start off by supposing that A is an element from A. And then here's your calculation bit. You want to unpack what it means to be in the set A, and then use some calculation and logic to build that to where you can repack what it means to be in B. And then you'd probably want to finish it off with a sentence like this. So A is an element from B, and thus A is a subset of B. And that would finish the whole thing off. Okay, so we're going to do maybe two examples of this. The first one will be this one. So we want to show that the set of all natural numbers that are divisible by 4 and divisible by 3 is a subset of the set of all natural numbers divisible by 6. So let's see how we could do that. So let's go ahead and suppose that we have a number m from this first set. In other words, it is a natural number that is divisible by 4 and divisible by 3. Okay, so right here I've just said that m is an element from this set, but now we'll unpack what it means to be inside that set. So that means that 4 divides m and 3 divides m. Okay, but now we'll continue to unpack. The definition of divisibility says that that means that m equals 4 times a and m equals 3 times b for a and b, which are natural numbers. Now next, we can see that the fact that m equals 4 times a, that means that m is even. 3 is clearly not even. So what that means is that b must be even. So let's write that down. So notice that m is even, thus b is even. Okay, great. So here in the background, we're using some stuff from number theory like the fundamental theorem of arithmetic. But since our goal here is to just learn how to write proofs, we can kind of take that for granted. Okay, so now since that b is even, that means that we can write b equals 2 times c for some natural number c. Great. Now we're ready to finalize our calculation. So maybe we'd say something like, finally, m equals 3b, which equals 3 times 2c, which equals 6 times c. Thus, m is in this other set. So it's in the set of natural numbers that are divisible by 6. But that finishes our proof. So I'll just like write down that that finishes our proof, but maybe you would want to finish that off with the phrase that this is a subset of that. Okay, let's do one more example of this. Okay, for our next example, we're going to have the setup that A and B are two arbitrary sets. Next, we're going to show that the power set of A union the power set of B is a subset of the power set of A union B. So again, we talked about the power set a bit earlier, but I want to recall that the power set is the set of all subsets of a given set. So power set of A is going to be the set of all subsets of A. Power set of B will be the set of all subsets of B. Okay, so we want to start off by supposing that we have an element from the left-hand side and then follow this general setup. Unpack it, do some calculation, and repack it. So let's do that. So let's suppose that capital X is an element from the power set of A union the power set of B, like that. Okay, nice. So next, we can use the fact that a union is like an OR symbol. So being in a union means that you are in one of those component sets. So that means X is an element from the power set of A, or X is an element from the power set of B, like that. Okay, but remember, what does it mean to be in the power set? It means you are a subset of that set. So maybe we would say, thus, X is a subset of A, or X is a subset of B. Okay. But next, we can use the fact that A is a subset of A union B, and B is also a subset of A union B. So let's recall that. So maybe we'll recall that A is a subset of A union B, and B is also a subset of A union B. So that's really easy to check, and we can actually just kind of take that as a fact. So this finally ends up with X is a subset of A union B. Just by subset containment, we either go through A or we go through B. But being a subset of A union B is the same thing as being in the power set. So X is an element of the power set of A union B. So let's see what we've got. We started off with X in the union of the power sets. We ended up with X is in the power set of the unions. So that finally tells us that the union of the power sets is a subset of the power set of the unions, which is exactly what we wanted to show. Okay, so now maybe we'll get rid of this and then we'll talk about set equality. We'll finish off this video with the technique of showing that two sets are equal. So let's just recall, by definition, the set A is equal to the set B if A is a subset of B and B is a subset of A. So in fact, we can use what we just talked about with showing one set is a subset of the other to show that one set is equal to another. That's exactly what we'll want to do. So let's say we've got the proposition, the set A equals the set B. Your proof has this general format. So you'll want to show that A is a subset of B. You'll independently want to show that B is a subset of A. And then you'd want to finish it off with a concluding statement like, thus A equals B. Okay, nice. We'll go through two examples. The first one is that this infinite intersection, so the intersection over all natural numbers of the interval minus 1 over n to 1 over n is equal to the singleton 0. So let's just sketch out what this is real quick before we look into the solution. Okay, so this is like the intersection of the interval minus 1 to 1. That would be like n equals 1. With the interval minus half to half, with the interval minus third to third, and then so on and so forth like that. Okay, so like I said, we need to prove that these two sets are equal, which we'll do by double containment. Okay, so let's see, we maybe want to do the reverse containment first, and so generally we'll sketch that like this. So in other words, we could write this in words as we'll show first that the singleton 0 is a subset of this intersection minus 1 over n to 1 over n, like that. Okay, so that's actually pretty easy to do. So let's suppose, maybe we'll call it x is an element from this singleton 0, but that tells us that x equals 0. But 0 is clearly on the open interval minus 1 over n to 1 over n for all n which are natural numbers. But being on all of those intervals means you're in the intersection. So thus, x is an element from the intersection over all natural numbers of these open intervals. Okay, good. So maybe we would finish it off showing that we have this singleton 0 is contained inside of this infinite intersection like that. Okay. Now next we want to show the containment in the other direction. This might be a bit trickier, so maybe we would sketch that out by just drawing a subset symbol in that direction. And then maybe we would write it out in words like this. Next, we show that the intersection of 1 over n to 1 over n is contained inside of this singleton 0, like that. Okay, so let's see how we could do that. So what we want to do is take an element from here and show that it must be equal to 0. Okay, so let's take an x in this intersection over all natural numbers of these open intervals minus 1 over n to 1 over n. But now notice that that tells us that the absolute value of x is less than 1 over n for all n, which is a natural number. Okay. But then from there, it pretty clearly follows that x has to be equal to 0. Because 0 is the only thing that can be made smaller than any positive number. So x is equal to 0. Thus, we have our containment in the other direction. So we've got this intersection of these intervals is contained within this singleton 0. Now notice this first direction was clear, so sometimes we would just say that this was clear and move on to the more interesting case. But since this is a whole class about writing proofs, you'd probably want to do both directions very carefully. Okay, we'll get rid of this and do one more example. We'll finish this off by showing that this union over all natural numbers of the closed interval from 0 to 1 minus 1 over n is equal to the half open interval from 0 to 1. And I've just sketched out a little bit of what this union looks like. So if n equals 1, we just get the singleton 0. Then if n equals 2, we've got that interval from 0 to half. If n equals 3, we've got that interval from 0 to 2/3, and so on and so forth. Okay, good. So let's go ahead and jump into this. So we'll start off by showing our containment in this direction. So let's go ahead and suppose that x is in the union over all natural numbers of this 0 to 1 minus 1 over n. Okay, so being in the union, especially an indexed union, means that there exists one person from that indexed union that contains this element x. So let's write that down. So there is some capital N, which is a natural number, such that x is an element from 0 to 1 minus 1 over capital N. So like I said, that's by the definition of the union. Okay. Next, we can see that 1 minus 1 over capital N is strictly less than 1. That makes this interval clearly a subset of 0 to 1. Okay, good. So notice we started off with x's in the union, and we ended up with x is in this half open interval. So that actually finishes off this direction. Okay, so now let's look at the other direction. So let's take it in that direction like that. So let's go ahead and suppose that x is in the half open interval from 0 to 1. But now we can notice that means that 1 minus x is between 0 and 1. So let's write that down. 1 minus x is strictly bigger than 0 and less than or equal to 1, like that. So it's strictly bigger than 0 because the only way it could be 0 is this, if that x was equal to 1, but we have a half open interval, so that is not possible. Okay, good. But we know that 1 over n can be made as small as we want. And so that's a consequence of the Archimedean principle. So what we want to do is find an n that fits 1 over n in between 0 and 1 minus x. And the fact that we have a strict inequality is really important here. So let's maybe write that like this. So let's take capital N, which is a natural number, such that 0 is less than 1 over capital N. So that's always the case, but it's also less than 1 minus x. Okay, good. Now what we can do is reverse this calculation a little bit to show that x is in an appropriate interval. So let's do that. So we can see now that x is on the interval 0 to 1 minus 1 over n. So that's just a reversal of this calculation. Okay, but notice that that is a subset of our union of these intervals of this shape. Good. Showing us that this half open interval is a subset of our union. So we could finish this whole thing off by saying that these two sets are equal. And that's a good place to stop.